today we're going to kind of shift gears a little bit. So up until maybe like the last 3 weeks or so, or for the last 3 weeks or so, we've been talking mostly about this topic of failure analysis. So we did falsification, we did the failure distribution, we looked at failure probability estimation, and now we're going to kind of switch gears to this sort of idea of formal methods, where we're sort of trying to more formally get guarantees on systems. So instead of trying to find failures or estimate probabilities of failure, here we're actually trying to prove the absence of failure. So under some set of assumptions, can we prove that our system will never fail? And we're going to do that mostly through something called reachability. And before I jump in, I want to give a disclaimer here. So over the kind of course of the quarter, I've been really concerned that there was just going to come some point where I just like run out of jokes to tell, and then I just can't entertain you anymore, because I'm just like, I don't know if I can keep this up. And so to be honest, we've now come to our point of reachability, and at this point, I don't know if that point has occurred, but I'm really reaching for some jokes right now. Wasn't sure if I was going to get booed off the stage for that one. Okay, so with that, let's get started on reachability. Okay, so most of the stuff that we've done so far has basically no guarantees with it. So we've been able to like search for failures and estimate these probabilities and whatnot. But if we, let's say, ran our search for failure for a long time and we didn't find any failures, that didn't necessarily mean that the system would never fail. It's just that we didn't necessarily find them. So that might be kind of unsatisfactory to some of you. And so today we're going to kind of switch over to this world of formal methods where we can actually start getting some guarantees on the behavior of our system. And specifically, with reachability, what we want to do is we want to compute the set of states that a system could reach over time. Okay, and so we're going to use this kind of very simple system that maybe some of you who have taken like controls classes or dynamics classes have seen before. Basically, it's a mass spring damper system. So we have this mass here. It's kind of square object. It's just like some mass. It's attached to a wall. And it's attached by this spring and this damper. And basically the spring acts like a spring that maybe you've seen before in the world. And then the damper is just something you kind of think of it like modeling air resistance or something like that. So this might look a little weird, but it's actually a very common model that's used for many physical systems. For example, like the suspension on a car. And so this kind of system often comes up in like control theory and things like that. And here we're going to say, so that this mass can kind of move back and forth along here. We're ignoring any idea of gravity. And then we're going to say it fails if it ends up in like this region. So if it gets too close to the wall or it extends too far, that's a failure. Okay, and so then let's imagine now that this mass is kind of out here and its actual resting position with respect to the spring is right here. So we've kind of stretched it out here. So let's say that we now let go of whatever it's holding on to as it's stretched out. What do you guys think is going to happen? Yeah, if you want me to do this, it's going to like oscillate back and forth. So that's what happens here. Okay, but we might not be satisfied with that. We might actually want it to like slow down a little bit faster or not oscillate as much. And so we could add some sort of controller to this, or in the terminology of this class, we could add an agent. And the agent is able to apply a force at this mass that can kind of counteract what the spring and the damper are doing. And ideally, it should like make it oscillate a little bit less. So if we look at what happens when we add this kind of agent, we get it to kind of slow down a little bit faster. So that's the system that we're trying to validate. And again, we don't want it to end up in these red regions. And to make things a little bit more difficult and kind of continue with the model of this class, we're going to assume that there's some sensor noise. So whatever agent is getting to apply the force to this mass doesn't get to observe exactly where the mass is, and it just has like some noisy observation of it with some like additive sensor noise. So if we add in some sensor noise, it's not able to do quite as well, but it's still able to kind of keep it in the center. But what happens if we add a lot of sensor noise? Then the whole thing might kind of go crazy and it does fail, etc. I had to add a lot of sensor noise to make this happen, so that's why sometimes you don't even like see it. It's like all the way out here or something. But the idea is that like at some point there's like too much sensor noise and the thing could fail. And so we might want to know like what is too much sensor noise? How do we know kind of how much we could have? And so maybe we ask this question like, given a bound on the maximum possible noise, can we prove that the system will never fail? Or maybe we want to provide a counterexample showing that a failure is possible. Because of course, if there is a failure possible, then we're not going to be able to prove that it can't fail. And so typically what these formal methods do is return a counterexample in that case that says, here's a trajectory where it does fail. Okay, and so we can answer questions like this using reachability analysis. So that's what we're kind of going to start diving into today. And to do this, there's kind of no free lunch here. So we, in like all the previous lectures, we were, doing all this failure analysis, blah, 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 but there were no guarantees that come with it. Now we're going to get guarantees, but we have to make some assumptions in order to actually get those guarantees. So one assumption that we're going to make in terms of the mass spring damper is we're going to say we always start the mass with a position between minus 0.2 and 0.2, whatever units you want to apply here, of its resting point. So we'll say its resting point's at 0, so we either like squish it minus 0.2 or we pull it out plus 0.2, and we're going to assume it starts with no velocity. So we imagine like we took this and we squished it and we're like just about to let it go, and it starts with no velocity there. And then we're also going to make an assumption that the maximum absolute observation noise on the position and the velocity is 1. So again, whatever units you want to apply here. But basically, we're bounding the amount of observation noise we could have. So we're bounding how wrong our observation could be about where what the true state of this mass is, what the true position and velocity is. And specifically, we can be off by at most 1, is what we're saying. So this would be like, let's say we have a sensor, we generally know how good it is, and we're saying we expect our sensor to be off by at most 1. So to kind of make these things more general, what we basically did was we just specified a bounded set of initial states, and then we specified a bounded set of disturbances. So more generally, with respect to other systems, these are kind of the general things that we need to assume for reachability analysis. Okay, so now let's look at what this kind of looks like. So here's, on this axis, we're showing the position of the mass, so that's kind of like where it was as it was going back and forth there. On the vertical axis, we're showing the speed of the mass, yeah?
And so we assume that we know exactly the model and have no dynamics noise or something like this?
Yeah, we're assuming we know the model and the only noise is on the observation. Yeah. We don't have to make that assumption. We could add noise elsewhere, but I'll show the more general formulation soon. Yeah. We do have to assume we know the model, though. Yeah. Okay. So we basically have velocity on the vertical axis, and then we're showing, I said that it's a failure if its position exceeds some value, so it either gets like too squished, so it exceeds minus 0.3, or it extends too far, so it exceeds 0.3. That would be like a failure, so in these red regions. And we're going to start in this kind of set of initial states where the position is between minus 0.2 and 0.2, and then we have 0 velocity. So what I've done here is just draw a bunch of samples from this kind of initial set of states. So this is kind of represents the set of states that we have at time step 1. And then we could imagine we just apply the dynamics for the system, which I haven't really showed you, to figure out where that mass could end up at the next time step. So here's all the position and velocities that we get at the next time step for all of these samples that we started with. And then we could just keep doing this for some amount of time. And let's say that we're just interested for some reason now in whether or not it's going to be safe at the first 4 time steps. So we can now see kind of what states it reaches over the first 4 time steps. But the thing here is like all we did was just run a bunch of samples. So we just did kind of basically a bunch of rollouts of depth 4. And we saw that none of the samples ended up in this kind of failure region, but that doesn't guarantee that the system will never fail. So again, like this is kind of just almost like we were doing falsification. We didn't find any failures, but that doesn't mean that it will never fail. And what we actually want to do instead is see if we can compute the full reachable set. So what is the full set of states that we could reach if we started in our initial set and applied these like bounded disturbances over time. So that's what these kind of shapes in the background are showing. And I'll get rid of the samples so you can see it better. So here our initial reachable set at time step 1 is just that initial set we started with. So we said we're always going to start at a position between minus 2 and 2 and a velocity of 0. So it's just kind of this line here. And then the next time step, we get this shape here. And this contains all possible states that the system could reach at time step 2. So I didn't tell you yet how to compute this. That's what we're going to be spending a lot of the lecture on. But that's the idea of like what a reachable set is. And then at time step 3, here's all of the states that we could reach, and at time step 4, and so on. Is there any questions up to this point? Yeah.
So you have here that like the shape of it is fairly well defined. Is it ever sort of a particle instantiated distribution, or should we always have our initial state set and disturbances should they all be in closed form? Like in terms of assumptions.
Yeah, so the question is kind of like the representation of the sets almost. Like these are all like nice closed sets. We're going to talk in this lecture about what nice set representation looks like. And I'll define it in a second, but really a set is just a collection of points. So in this case, it's a collection of an infinite amount of points, and we have like nice ways to describe that. But sometimes you could just write down a set as a collection of points, and it's kind of up to you how you want to define those things. Yeah.
So the lecture is called Reachability for Linear Systems, but in assumptions you didn't specify it, but I'm sure we need to put some kind of linearity constraints or some continuity constraints on our models, right?
Yeah, so the question was about linearity. In this lecture, we are going to assume that, but for right now, I'm just talking about what reachability is, and then we'll talk about, when we talk about how to compute these sets, I'm going to give you methods this lecture for linear systems, and then next lecture we'll talk about nonlinear. Okay, so let's recap our goal, kind of more generally and with some added notation here. So, all right, a yellow slide to wake you up. So we're gonna assume some things. And the first thing that we said we assumed when we did all of this stuff is that the initial states come from some bounded set, so some bounded initial set. So that was, in our case, like what positions could the mass start at and what velocities could it start at. And then we're also going to assume that the disturbances at each time step come from a bounded set as well. So in this case, in our case, it was like the amount of observation noise we apply came from some bounded set. Okay, and then specifically to write this set down mathematically, it looks a little crazy here, but all we're saying is like there's a component of this set for the agent, environment, and sensor, and each of those comes from its own set specifically. And as we were kind of talking about, a set is just a collection of points. So it could be an infinite amount of points. For example, a rectangle contains an infinite amount of points, but we know that that's still kind of a bounded closed set. Or it could just be a set of points. That's it. And so for the mass spring damper, we basically assumed that our initial set was all states with a position between -2 and 0.2 and no velocity. And then for our disturbances, we don't have any disturbances on the environment or on the agent. So these are what we just call the zero set. It's more just like a notation thing, but like basically these just don't get used because we don't have disturbances on the agent or environment for this system. But for other systems, we might. But where we do have disturbances for the mass spring damper is on the sensor. And so this kind of big XO set is going to be all noise values between -1 and 1. Okay, and then you might be thinking though, but like all these problems that we saw before in this class, they've always had distributions over initial states and disturbances. And you know that's different from these sets. Like we introduced the mass spring damper with this, but like what about the pendulum? It had like a whole distribution over initial states and disturbances. And so what we could do is we can convert these distributions to bounded sets by using their support. So basically everywhere that the distribution is non-zero, we include that in our set. So for example, if we had a uniform distribution between -1 and 1 like this, the support of that is -1 to 1, so we get a bounded set. But then some of you are probably like, well, most of the time we had Gaussian distributions, their support is infinite, they're defined over the entire real line, so that's not going to give us a bounded set because that's going to be, you know, all possible values. And so what we could do is we could just select a region that contains most of the probability mass. So maybe we go out like 3, 4, 5 standard deviations and just cut it off and say that's, you know, good enough. But this is an assumption you need to make. Yeah.
Zero set part again?
Yeah, so this is basically just like a set such that when we apply operations to it, it kind of acts like zero. But really all I'm trying to say is like there are no disturbances on the environment or the agent for the mass spring damper. And so it's just kind of like a placeholder for the disturbance set, meaning like there just aren't any. Yeah.
So this is just a property of our system that we're working with, not
This like zero set thing?
Yeah.
Yeah, so everything in blue is like with respect to the mass spring damper system. Everything in black is like the general case of things.
And again, to reiterate, zero set is second continuum.
Whoops, sorry. Zero set, it's like,
Second continuum is zero.
I'm gonna, maybe. I'm actually not sure. Like basically in the code, we use an object called zero set from the package we use. And it like has the properties of zero we need when we apply set operations. I would have to like look up more details of like what exactly is meant by the zero set so I don't tell you the wrong thing. Yeah. Okay, so we made these assumptions. And now, given these assumptions, what we want to do is compute the set of reachable states at some particular depth in our trajectory. So here's what that looks like mathematically. And so basically what we're going to call this kind of fancy script R sub d is all states that we could reach at depth d if we were to start from an initial state in our bounded set of possible initial states and select the disturbance at each time step from some point in our disturbance set for that time step. So basically we're just saying, what is the set of states we could reach if we make these assumptions up here? And so what all this math is saying is that it's just saying the set of all states for which the state could be reached given some initial state and disturbance set, where that initial state and disturbance is drawn from our sets that we specified over initial states and disturbances. And so like all this reach function is doing is it's doing a rollout starting from state S with these set of disturbances and giving us the final state at that depth. What questions do you have on that? What's up?
So it is kind of a rollout.
Yeah, so basically it's saying like, if we were to do a rollout from all possible points in our initial set up to depth d, what is the set of states we would end at for that rollout?
Is that how you reachability?
So I'm gonna probably get to this in a second, I think, in the slides, but basically like, if you try to do that, like if you start an initial set with an infinite amount of points in it, you have to do an infinite amount of rollouts to figure out what that reachable set is. And so kind of the whole key to today's lecture and the next few lectures is like more efficient ways to handle that. Yeah, a good question. Any other questions here? Yep.
Can you explain the depth concept?
Yeah, so the depth is basically just the number of steps in our trajectory. So if we want to say like, what is the set of states that we could reach at time step 4? It would be R sub 4.
Oh,
Yeah. Yep.
But this assumes that there is a finite set of things in each set.
S and X need to be bounded sets. Yeah.
Okay, so they're bounded sets, and then naively computing this is intractable. Is the idea?
Yeah, it is intractable to do a bunch of rollouts.
Okay.
Yeah. Okay, so going back to our mass spring damper example, just like adding this notation to it. So R sub 1, so the reachable set at depth 1 is just our initial set, so it's just this line that we had. And then R2 is the set of states we could reach at time step 2, and so on. Okay, and then a lot of times though, we don't just care about the reachable set at a particular depth, so we're not just like, oh, what is the set of states I could reach at time step 4, and that's all I care about because I don't care what my system does at all other time steps. That's kind of unlikely or not what we typically want. Typically we want the reachable set up to some horizon. So you want to say like, what are all the states I could reach between now and time step 4, not just at time step 4. And so we just denote that R1 through H, so all the sets up to H, and it's just the union of all the sets at each depth. So basically what you can imagine is we have the reachable set for each depth. We just take the union over all of them, which kind of just looks like us stacking them all on top of each other. And now we can say these are all the states we would reach if we operated our system from time step 1 to time step 4. Yeah.
So it looks like previous time steps or the states of the previous depth may not necessarily be a subset of what you have at a later depth. Is that
Yep, that's actually absolutely right, yeah.
okay? But when you're doing this union right here, you're including everything.
You're including everything. Because if I like came up to you and was like, hey, I want to make sure my system's never going to enter this red set between time steps 1 and 4, you wouldn't want to look at just one of those time steps. You'd want to look at all of those time steps together and be like, does anything in that kind of union set intersect with this bad set? Yeah.
Apologies, can you just explain the notation of reach again?
Sure. So this is just as if you took, you started in state S, and then you used this set of disturbances for each time step, and you did a rollout, and then you took the final state that you ended up with in that rollout at depth D.
I see. Okay, that makes sense. Great.
Yep.
Is it okay that it's not continuous, like the union of all the sets?
This one I think it is kind of continuous, but it's not convex.
Or is it
Um,
the very first like connection is just a line?
It's just a line, yeah. So that basically makes it non-convex, which is okay, but it kind of depends what you want to do with it. So if you have non-convex sets, they're generally more difficult to work with. So for example, for your project, like we were trying to compute the volume of this non-convex set. That's kind of hard to do. So if you wanted to compute the volume of your reachable set, then that might be an issue. And so it really just depends on like what you want to do. And I think as we kind of go throughout this lecture, we're going to see some sets that have very nice properties, such that if we want to do all these things like compute volume or some other operations I'm going to talk about, we want to use sets like that. And then you're kind of limited if you have these like non-convex sets. Yeah, good question. Okay. Okay, so we have the reachable set. Now what, we've kind of already talked a little bit about this, but basically we want to see now if it intersects with any bad states. And if it doesn't, then we can say we're never going to end up in a bad state, and so we're good to go, our system is safe. And so we're going to call our bad states in this class the avoid set. It's basically the set of states that we want to avoid. So that does mean that you have to have your safety property or your specification written in terms of a set of states that you want to avoid, which is not always possible. But we did talk a little bit about reachability in the property specification lecture. Okay, so in the case of our mass spring damper, we wanted to avoid the states that were in this red region. So these two kind of bars make up our avoid set. Okay, then there's one other thing you might be thinking, well, maybe we don't always want to avoid a certain set, maybe we want to reach a set. So that's kind of more liveness than safety, but you might also want to check if a system reaches a goal region. And you could do that by checking if the reachable set is contained within the goal region. So you want to say like, all the states I could reach end up at the goal. We're not going to talk about this case quite as much in this class, and in the book we don't talk about it as much, but something to keep in mind if you did want to reach a goal region instead of avoid a bad region. Okay, so now I just kind of explained at a high level what reachability is, and now I want to talk about how we actually compute these reachable sets, and specifically we're going to focus on the math behind computing reachable sets for linear systems, and then in subsequent lectures we'll talk about what to do for nonlinear systems. Okay, so plan for today, we just talked about reachable sets. Next I'm going to define exactly what a linear system is. And then we're going to spend a good chunk of the time on this idea of set propagation techniques. So there's kind of multiple ways to do this reachability for linear systems. One is set propagation. And then the last one, which we'll talk about a little bit at the end, is using optimization. Okay, so let's dive into linear systems. So linear systems are basically a class of systems where the sensor, the agent, the environment are all linear functions of the state, action, observation, and disturbance. So they're just all linear functions of their inputs. So previously we, kind of just generically defined the observation model, the agent, and the transition model, and now we're going to specify that they have to have this particular functional form. So for example, for the observation model, it's a function of the state and the observation disturbance, and we're saying it needs to be a linear function of these things. So it needs to be some matrix multiplied by the state, plus some linear function of the observation disturbance. Similarly for the agent, this kind of big pi O is a matrix multiplied by the observation and so on, and then similarly for the transition model. So what this looks like for the mass spring damper, which turns out that's the whole reason we introduced it, it's a linear system. And basically what's happening here is our observation model is just the identity matrix, because our observation is just the state plus some noise disturbance, so plus some added noise. So this kind of big boldface O is just the identity matrix in this case. Our controller is a proportional controller. You don't really need to understand like how we got any of this. You can take dynamics or controls if you want to look into this. But this big pi O is just equal to this matrix. And then, like I said, the agent and the environment are deterministic for the mass spring damper, so we actually don't have a disturbance on either of these. And then the transition model is kind of these matrices multiplied by the state and the action. And again, this is just given to you. You don't need to know how to derive this or anything. So that's linear systems. That was a short section. And now we're going to talk for a while about these things called set propagation techniques. So I put these equations back up here because we're going to need them in a second. And let's look at a single time step first. And let's try to write our next state, S prime, in terms of our current state and the disturbance that we apply. So we can start by saying, okay, our next state is equal to our transition model evaluated at the current state with the action that we take and our disturbance. But we don't want it in terms of the action because we just want it in terms of S and X. And we know that the action is going to be the result of whatever policy we applied. So we can just take this action and replace it with our policy function. So now we're just saying it's the state, the action that comes out of the policy, and then our disturbance still. But we don't want O in there either. And we know that O is just the observation that comes out of our observation model. So we can just replace O with our observation model. And then we get this kind of big thing of nested functions, but this gives us basically the next state in terms of our current state and the disturbances that get applied. And then all I'm going to do now is we have functions for all these things. So like we know OSXO is equal to this function for a linear system, and so on. So I'm just going to plug all of those things in, and we get something that looks like this. And then I'm just going to do a whole bunch of simplification, just kind of group some terms together, and we end up with this expression. So now we know that our next state is equal to this expression here, which is, this just ends up being kind of a big matrix multiplied by our current state, plus some other matrices multiplied by our disturbances. And the thing, you don't really need to study this equation too hard as long as you kind of understand where we got it from. But the big idea that I want to get across here is basically what's going on is we're taking some matrices, we're multiplying them by some vectors, and we're adding stuff together. So those are the main operations we had to do to calculate the next state if we were given the current state and the disturbances. Okay, but all of this is kind of applied to a single point. So we just said we have our current state, that's just one state. We have our current disturbance, it's just one disturbance. But we're interested now in what happens if we have a whole set of states? What happens to a whole set of states, given that we could have this whole set of disturbances? And so what if we could just take these operations, and instead of applying them to just a single point, just a single state and disturbance, we could apply them to entire sets. So that's kind of where we're headed. And now we're going to talk about kind of what it means to do that and how we do that. But this is really just the main idea behind set-based reachability. Okay, so again, we now have this expression that we need to evaluate, and we want to evaluate it over sets. And what's going on in this expression is we have some matrices, and they're being multiplied by some vectors and adding. So there's basically two main types of operations that are required to kind of compute the next state for a linear system. And one of those operations is matrix multiplication, or sometimes we also refer to that as a linear transformation, meaning same thing. And then the other one we saw is addition. So if we could just define what these operations mean for sets, we could then take this equation and convert it to be not just over single points, but over sets. So that's where we're headed. Okay, so let's talk about what matrix multiplication looks like for sets. So here's kind of the mathematical definition of it. So say we have some set. So by the way, as you're kind of parsing through these slides, when we use this kind of script math-cal notation, that typically denotes a set. So when you see a nice fancy curly letter, that probably means it's a set. And then these bold-faced things are matrices and vectors. So let's say that we want to take the set P and multiply it by some matrix A. Then all we do is take every point P in the set, multiply it by A, and then the set of new points we get by doing that would be our new set. So we can see what this looks like to make it a little more intuitive. So let's imagine we have this set here. We'll call it P. we're going to multiply it by this matrix, so this is equal to A, and then over here we're going to show what the result is. So all this is saying is that we take every point in this set, so let's just take this point for example, we take the value of this point here and we multiply it by this matrix. That'll give us a new point, and that's going to be in our new set A times P. And then we can repeat this process basically for all of the points that are in P, just continue to multiply them by A, and then eventually we can kind of take all of those points and that's our new set. But in order to get this kind of purple shape, we would need to compute that for all infinite points. So we need to take every single point in P and get the result to create this kind of A times P. But of course, we don't have time to do that for an infinite set of points. And so it turns out that many common set representations, like this set, like a rectangle, etc., they have efficient ways of actually doing this transformation without having to take every single point in P and multiplying it by A. And we're going to talk about how to do that later in this lecture. Okay, so the next thing, we now know how to multiply a set by a matrix. Now we need to know how to add two sets together. So here's the mathematical definition for this. You can ignore this fancy sign for a second here. But basically when we add two sets together, we take every point in set P, so we're adding set P to set Q. We take every point in set P and add it to every point in set Q, and then the result is our new set. So by the way, this kind of fancy plus symbol, it's just kind of the symbol we use for addition for sets, and it refers to a Minkowski sum. So that's what this operation is often called, is a Minkowski sum. Okay, so let's see what this looks like. So let's say that we want to take this set P and add it to this set Q. And so what we need to do is for every point in P, we take another point in Q, and all I'm going to do is draw vectors to these points. So these vectors represent basically the same thing as the point, I'm just looking at the vector version. And if we want to add these 2 points together, we just add the vectors together. So we take this vector and add it to this one. And then we'll get this new point that's going to be in our set P plus Q. So we get this purple point here. And then we can just repeat this process. So we grab another point from P, another point from Q, draw the vectors, add them together, and then we get this new point. And then we can keep doing this over and over and over again. Imagine we did it an infinite number of times, and we would get the set P plus Q. Yeah?
Do you know which points to add? Or is it like you're doing every combination?
Yep, every combination. So this is intractable because there's an infinite number of combinations, but there's like ways I'm going to talk about later that you can do this without having to do every single individual point. But just to kind of understand what this operation is, imagine if you could do that, that's how we would get this set. Okay. So yeah, like I just said, many common set representations like hyperrectangles, etc., they all have efficient ways of actually doing this calculation without doing all the individual points. Okay, so now we know how to do these operations. So let's look back at our equation we had before where we had all these matrix multiplications and pluses and see if we can do this for sets. So all we need to do now is just replace those operations with set operations. So we're just going to now multiply matrices in the way that I showed, and then we're going to replace the sums with Minkowski sums. And now, given an initial set and these disturbance sets, we can calculate the set of possible next states. So this is kind of the big equation that we're going to use for set propagation for linear systems. Okay, and so here's what this looks like in code. So in the book, we implement it like this. We have this kind of get matrices function, which just takes in a system and returns the linear matrices for the system. So we need like TS, TA, pi o. So it just returns those matrices. And then when we do this propagation, we take in our current set and the set of disturbances. We grab those matrices for the linear system, and then we just implement this line here in code. And here's your add for Julia. Look at this amazing little O plus. It looks just like this. These like script things, everything, it all just looks like this, which is pretty cool. And the reason that we can do this is because of this wonderful Julia package called lazysets.jl, which I think a lot of you will become quite familiar with during your project. And it's amazing. Like, we can just do this. We can just like multiply sets using like all the normal stuff. We can do this O+, it'll do them in Minkowski sum for us. It'll just do all the stuff for us. And we're gonna kind of throughout the next few lectures show more and more features of what lazy sets can do as we teach these concepts. And like, it's just so good. So there's your ad for Julia. And I don't know, if the lazy sets people end up somehow watching this one day, thank you. Your set or your package is just wonderful. Okay. So that was how you do it for a single time step. But now let's talk about how we would do that for multiple time steps. So basically, as you might have already been guessing, like we could just keep applying this equation. So we had an initial set, we had a set of disturbances that gave us our next set. So we could just make that our initial set and then just kind of keep going in order to get the reachable sets at future time steps. So all that looks like is this, where basically all we just did here is we just took the initial set and said that's gonna be our set at the previous time step or the previous steps, and then our next set is going to be the set that we're trying to compute for the current depth. So we basically just keep applying this equation over and over again, and we can build out the reachable set over time. Okay, so let's see what this looks like in a Pluto notebook. Before I go over to that, are there any questions? Yeah.
So the reachable set and the current set of states is the same thing, but don't we need to add them, just like squish them down together?
So there's kind of the subtle difference in notation we made for the book, which so RD represents just the set of states we could reach at depth D, so only at D. And then if we say R1 through H or R1 through D or whatever, like R1 through 4, then we would squish them all together. Most of the times what we care about is like R1 through 4.
Is there any distinction between saying that these are the reachable sets versus just like the states at D?
Well, it's the states you could reach at D, right?
Oh, given some initial state, I guess.
Yes. Given some, yeah. So for all of this, we are assuming that there was some initial set that we cared about and some disturbance set that could be applied at each time step. Yeah, no problem. Okay, so let's look at what this looks like. So basically what's going on here is this is our same plot that we had before. We're gonna, in a second going to control kind of the magnitude of the noise. And then what I'm showing here is the samples. So these blue things are like the samples. You can ignore the big green rectangle for now. But the blue things are the samples. So again, we're starting between -2 and 0.2. And you can't really see it right now because the set is just a line, the initial set. But you'll be able to see the sets as we kind of go for future time steps. So for example, let's go to the second time step or the third time step. And now you can see this set here is our reachable set at the third time step. So here's all the samples. We know that those have to be contained within that reachable set. And then we've now computed this set by applying the Minkowski sum and linear transformation and all that stuff at the third time step. And so we can just kind of continue to do this for a while, and we can understand the set of states that the system could reach over time. And you guys will get to play around with this and all of these cool graphics in your project 3, so hopefully you'll enjoy that. Okay, so this all looks good, and what's cool is that this doesn't intersect with our set that we wanted to avoid, so this feels good. All the way up to time step 21, we are safe. But let's imagine that we increase the magnitude of the noise. So we're now making the system, a little bit more difficult to handle because we have more perception noise. And as we kind of continue to increase that, we get worse and worse to the point where now our reachable set actually, by the 20-something time step, it actually intersects with this set that we were trying to avoid. Yeah.
So do we actually know, if you reduce a little bit the noise maybe, you draw like this kind of green inner, set.
Yeah.
So you need some equation for the boundary of the set.
Mm-hmm.
And do we get like an exact form of this equation out of the code automatically?
Yes, we get an exact form for this equation. I'm going to talk about, to get an exact form, you need to have like a certain type of set that you start with, but I'm going to talk about how to get that. Yeah.
Cool.
Yeah, and also this system is linear. So for nonlinear, we're not going to be able to get
this
that.
is obviously not a nonlinear boundary. So
It's not a nonlinear boundary, but
I'm
it's fine.
excited.
Good, I'm glad. Yeah.
Yeah, I guess maybe you're going to touch on this, but it's like, what, right now this seems like it's just a set of particles that we're propagating. So what is the property of the set that it must contain so that we can do this properly?
The property.
Like, what properties does the set have to have for it to actually work?
We're gonna get there.
Okay.
Okay, so yeah, but then basically the other point I wanted to make here is like if we get our noise super high and it turns out like we do now overlap with this set that we don't want to, basically what's going on is like all of our samples, so we just ran a bunch of rollouts, all of our samples don't look like they intersect with this set, but again, we couldn't just conclude from the rollouts that our system was safe, and it turns out that if we kind of do this exact reachability, we find that there is actually some rollout where it's possible that it enters kind of this set that we wanted to avoid. And so our reachability is able to conclude that this system is unsafe, whereas when we just did a bunch of rollouts, we didn't actually observe this behavior.
What I think is confusing is that we're not taking a convex hull of the samples.
Right, yeah.
We're taking the max initial state. So it's not the samples, it's the max.
And then we
initial
just
state.
happen to plot some samples for fun.
Yeah.
Yes, yes.
Okay, got it. Great, yeah.
Thanks for pointing that out. Yeah.
Yeah.
So these samples are completely independent from how we computed this. It just so happens that when we do this, we know for a fact, since this needs to include every possible reachable state, all of our samples must be inside of it. But this is just the result of running a bunch of rollouts.
Yeah, that makes sense.
Yeah, thanks for pointing that out. Yeah.
So far, I think we've discussed how we can check that our reachable set will there be a future state that possibly violates our safety, but do we actually have a way to figure out what sequence? Will we discuss techniques to figure out what sequence of disturbances in the initial state will bring us to that failure?
Yeah, that's a good question. I think from the set-based technique, it's not super obvious how to get that counterexample. Some of the other techniques we discuss, it's possible to do that. But yeah, that's a good question. I'd have to get back to you on that. Yeah.
I mean, if I understand this question correctly, I guess not every point in this set that we find is actually reachable, right? We could have we have an over approximation of all the.
No, this is the exact
The same
set
thing.
of reachable states. It's not an over approximation.
Okay.
Yeah. Okay. So let's go back and see how we do all of this, because maybe that will clear up some of these questions here. Okay, so let's talk about, before we get into how we actually do this, let's just recap kind of what kind of guarantees we can get here. So we computed the reachable set out to some depth, so here R1 through 4, I just showed you R1 through 21. And if we find that R1 through H does not intersect with the avoid set, then we can guarantee that the system will not enter the avoid set from time steps 1 to H. Okay, but after time step H, there's no guarantees. So we basically just only said that for time step 1 through 4 in this case, or what I just showed you, 1 through 21, we know it's safe. And so you might say okay, if we go out to a sufficient time step that we know our system's not going to be operating longer than that, then we're good to go. But for infinite time, there's no guarantees here. All we did was compute it for 1 through H. But there is one case where we could get a guarantee for infinite time, and that'd be if we get something property like this. So this might take a few kind of back and forth through your head a few times, but I'll try to say it once here. Basically, if we have, this is our reachable set at one time step, and then at the next time step, we get a reachable set that's fully contained within the reachable set that we had at our previous time step, we're basically saying all states in this set have to go to some state in this smaller set. And since this smaller set is inside of this set, it must be the case that all states in this smaller set will also stay within this smaller set. So that might need a few times through your head, but basically the idea here is that if we do happen to get a reachable set that has this property, there's no guarantee that we would end up finding this. But as we're going out and computing these sets, if we do get something that has this property, we can say that R sub D is an invariant set, and the system will stay within R sub D from there on out indefinitely. Yeah.
I'm wondering, is the requirement even more lax than this? That we really only need to be a subset of our reachable set over the time horizon from our start.
Yeah, you're exactly right. So the question was, is it even more relaxed than this? And that's true. You could actually say replace this with 1 through D minus 1, I think is what you're saying. And we did realize that when we were writing the book, actually, and we actually implement this in the book, and the main problem is, kind of as I was pointing out earlier, this set tends to be non-convex, and it's very difficult to check if a set is a subset of a non-convex set. So yes, if you have that property, you can draw this conclusion. It's just really hard to check that property.
And maybe just another quick thing. So I'm thinking that it should be RD minus 1, that should be the invariant set, not RD. Since we know that.
No, because it's basically everything in here we know goes to RD,
Right, but there's
and RD is in here,
Yeah.
so everything in RD also has to go to RD.
Yeah, that's true eventually, but it can go out to RD minus 1 before coming back to RD. I think.
Oh,
I don't think so.
Okay, maybe
Yeah.
I guess maybe the point is that it has to hold for all D.
Oh, I see. Sorry, I made a mistake in thinking about
Okay.
this.
Okay,
Is that true?
what has to hold for
You
all
have
D?
to show it to prove this. You have to prove it for all D.
You just have to have this happen at some point, and then you can say from this point on, it's going to be in this set.
I don't get that.
So we know that everything in RD minus 1, so let's say that this was the reachable set at time step 5, was this outer thing. At time step 6, all of these states must be in this rectangle. So at time step 7, well, this rectangle was in this rectangle. So, and we already know that everything in this rectangle goes to this one. So then everything in this one also must go to that one at time step 7. And then we're just going to keep having that happen for all the rest of time.
Right.
Yeah. Yeah.
Is there an example that can help us understand this physical system?
Sure. So let's say that we were looking at our mass spring damper, and it was kind of oscillating for a while, and then eventually it's kind of settling towards the middle. You're probably going to end up getting a set such that the position and velocity keeps getting, the amount of reachable positions and velocities will keep getting smaller and smaller because you're settling on the middle, and so then you'll probably get a smaller set of possible positions and velocities at one time step than at the previous time step. So, yeah.
This seems like something we put into domain knowledge and express in a mathematical format, but vice versa, or?
Well, you don't necessarily need domain knowledge. I mean, because I'm saying, there's no guarantee you're going to get this property. So domain knowledge might help you have a hint that maybe this would end up happening, and you're kind of hoping most of the time when you do this that this will end up happening, so you can get an infinite time guarantee. But really, after you compute your reachable sets, you would just need to look through them and see if you have this property happening. Okay. And these are all with respect to the assumptions that we made about all the initial states and disturbances. So don't forget, we got a bunch of guarantees, but we also assumed a bunch of things along the way, so you should always keep that in mind. And to really drive the point home about assumptions, I've got a story here. So we're going to go back to COVID, which is somehow almost 5 years ago now. And so at the beginning of COVID, I really didn't know, like many of you, I had no idea what was going on, and I was like, I don't know what to do. So I ended up going to my boyfriend's apartment, who's now my husband, and we're like, oh, it'll be 2 weeks, fine, we'll just move in for these 2 weeks. Ended up being forever. And this is after 8 months of dating, in a studio apartment. And I was kind of like, okay, well, we gotta figure this out, we gotta both work, whatever. So it's a studio apartment, so he had a desk near the bed that he was working at, and I was left with this kind of tiny kitchen table that he had. And this was he was, before this period of time and before work from home, he was basically living at his office. So he was eating breakfast, lunch, dinner there. So this apartment was not really livable. He didn't really live in this apartment. And so all he really had for his tiny kitchen table was a folding chair that one of those chairs you'd put out at a party when you don't have enough chairs for everyone else. It was that kind of chair. And I was like, okay, there's absolutely no way I can work from this folding chair all day, every day. My back was already starting to kill me. And so I was like, okay, I need to go ahead and order a chair. And so I went on Amazon and found a chair for myself. And so I found specifically this chair. And I was like, it's totally bachelor pad at this point, might as well spruce it up with a nice hot pink chair in the middle of the apartment. So I ordered this desk chair, and I didn't really know what reasonable prices for desk chairs were, but I looked at this and I was like, wow, this is super reasonably priced. Perfect, I'll just order this chair. So I ordered it. You see March 17th, 2020, pretty crazy time. And so then the chair comes a few days later, and I'm all excited. I get the notification it's there. I run downstairs. I'm like, yes, no more of this terrible folding chair. And I go downstairs, and the box is about this big, maybe. And I'm like, weird. Like, I feel like a chair shouldn't fit in that, but maybe it's just in a lot of parts. Like, okay. So I pick up the box and I'm like, wow, this chair is really light. I must have bought like some like really nice like light chair. Get upstairs, open the box, like still convinced that this is a chair. And then, yeah. Wasn't a chair. And in fact, it was just these two pieces of cloth. And so you can see this is about the size that the box was. There was like no way that there was a chair in that box. And I was just stuck now with this folding chair with some hot pink cloth on it. I don't know, probably like $20 or something. There was a lot of...
Again.
I have not ordered it again. But these covers are actually still on my husband's desk chair. He really liked them and took them for himself. So, but yeah, so that was a bummer. I had to wait a few extra days for an actual chair to come, which I made sure to really check the next time. And the key thing here is that I just assumed that if the picture of the item is a chair, that it is in fact a chair, but you should always read. So always read the fine print. Assumptions matter, or in this case, always read the extremely large, obvious print. Because if I had really just read anything, I probably wouldn't have been in that situation. So there you go. Make sure you're always keeping track of your assumptions. Okay. Back to set propagation techniques. So we were talking earlier about how if we want to do like matrix multiplication, and we ran into a similar thing with the Minkowski sum, that if we have like this whole infinite set of points that we now need to multiply by a to get this new one, we can't do that. We don't have time to do infinite points. And so there's like these common representations that have efficient ways of doing this. And so now let's talk about like what actually are these nice set representations. Okay, so first I'm just going to list some properties that would be nice for our sets to have, and then I'm going to show you some sets that have these properties. So one nice property for a set would be a finite representation. So I don't have to sit down and tell you every single point that's in the set. I don't have to be like 1.1 is in the set, and 1.2 is in the set, and 3 is in the set. We can just specify something like, maybe for a rectangle, I could just tell you the corners of the rectangle and you would know every point that's in the set. So you want to have some sort of finite representation like that so we can tell you the points that are in the set without having to list them all. Efficient set operations, so we've already talked a bunch about this. We want to be able to compute that linear transformation or Minkowski sum or intersection or union without having to just apply it to every single point in the set. And then finally, sometimes it's nice to have this property where things are closed under set operations. And what that basically means is if I apply an operation to a set, I get a set of the same type out. So to give you a concrete example of that, like the intersection of two rectangles is also a rectangle. So for example, if we have these two pink rectangles here and we look at their intersection, that intersection is also a rectangle. And so we say that rectangles are closed under intersection. And just a little test for you, are rectangles closed under union? I see a thing. Yeah, no, they're not closed under union, because now we're looking at, what is this whole space here? Well, that's certainly not a rectangle, so they're not closed under union. Okay, so those are nice properties to have, and what are sets that have these nice properties? Convex sets, they tend to be quite nice. A convex set is defined by kind of this equation here, but I think rather than looking at all the math, the easier thing to do is kind of just look at what it means visually. So a convex set is a set such that if you draw a line between any 2 points in the set, that line will be contained entirely within the set. So I can pick any 2 points in here, draw a line between them, and that line's going to be in the set. But then if there's some way to take 2 points in the set and draw a line between them, and that line is not contained within the set, then our set is not convex. So this set here is convex, this one is not convex. And specifically, we are big fans of polytopes in this class. So we're gonna mostly be talking, so there's other types of convex sets, there's like ellipsoids and circles and things like that. In this class, we're mostly gonna talk about a convex set called a polytope. And if you wanna know about those other cool types of convex sets, you can take convex optimization with Stephen Boyd, and it's his birthday today, so if you happen to see him, you can wish him a happy birthday. Okay. Oh, did you want a picture of that?
Yeah, go back for a sec.
Do you want to film the fireworks?
Yeah, fireworks too, please.
Okay, ready?
Yeah. Thank you.
Okay. Okay, so to talk about what a polytope is, which we're big fans of, let's build out a polytope. So polytopes are made up of these things called linear inequalities. And a linear inequality just is an inequality with this form. So A and B are just vectors, and this is a constant that we pick, and X is our variable. And so we're just saying A transpose X less than or equal to B. That's a linear inequality. And if we actually see what that looks like visually, we can basically plot the line A transpose X equals B. So here we've picked values for A and B. We're going to call them A1 and B1. And this line represents the equality part of it. And then everything on this side of the line is points that satisfy that linear inequality. And we call this kind of space of all the points that satisfy the inequality a half space. So this, it's not bounded, it's infinite, it extends, far off of this plot here, it extends, forever in space. And so you can kind of think of this as like dividing all infinite space in half by kind of cutting through it with this linear inequality. And then if we have multiple linear inequalities and we take the intersection of them, so we're taking the intersection of half spaces, then we get a polyhedron. So the idea here is we now have a linear inequality with A1 and B1. We pick another linear inequality defined by A2 and B2. These are the vectors A1 and A2. And we take the intersection of those, now we have a polyhedron. So it's not bounded, but it's more than kind of just a half space. So we have this shape here now that extends, forever into infinity. And then if we intersect enough of these and we get a bounded intersection of half spaces, then we get something called a polytope. And so the way we tend to represent polytopes, at least one way, is by just kind of stacking these inequalities on top of each other and saying that all of these inequalities need to be true, and then we get this kind of bounded intersection of half spaces. Yep.
Can you formally give a definition for what bounded is? I know it's thinking of box.
I'm sure someone can, but I cannot.
Sounds
Yeah.
maybe bounded in like a norm sense, like all the points in the set have to have some norm that's bounded.
Sounds good. Yeah. Okay. So, talking about polytopes, there's kind of two different representations of polytopes that we'll talk about in this class. One is an H polytope, so that's the representation we were just talking about. So you can think of H being for like half space, and it's just a set of half spaces. And so for this matrix A and this vector B, you imagine we just stacked all of the A's for each of the linear inequalities on top of each other, and we stacked all of the B's on top of each other. And then the polytope is just the set of points that satisfy this inequality. There's also another representation that's sometimes useful called the V polytope. So you can think of V for vertices. And we talk about a V polytope as a convex hull of a set of vertices, so written like that. And the convex hull of a set of points, so for example, this set of points here, is just the smallest convex set that contains all of the points. So the convex hull for this set of points is kind of this set here that's defined by these points here. And so when we write down the vertices of a V polytope, we really only need these points that define the convex hull on the edge. So a lot of times we just write it down as this set of points. These are like the vertices, basically, for the polytope. So the way you can think about it is there's two ways to represent polytopes. Actually, there's more than two ways, but the two ways that we're going to talk about in this class are the H polytope, where we have an intersection of half spaces, or the V polytope, where we just specify its vertices. And both of these are equivalent. So you could take a V polytope and convert it to be represented as an H polytope and vice versa. It's always possible to represent it in both of these ways. Just sometimes one way is like more useful than others. And specifically, a V polytope is quite useful for doing things like linear transformations and Minkowski sums. So we're going to look at this V polytope idea and talk about now how do we actually apply this set operation without doing all infinite points to the polytope. So let's say we want to multiply this polytope by some matrix A. It turns out it has this equation. But let me just visually show you what happens here. So let's imagine we have this polytope here. It has vertices V1, V2, V3, V4. And basically we're saying that the new polytope is the convex hull of if we take A and we multiply it by each vertice. So all I'm going to do here is multiply each vertice by A. That moves the vertices to some new points. We connect them together to get the convex hull. And then this is the resulting set of A times P. So we didn't have to take all infinite points in P and multiply them by A. Turns out we just had to multiply the vertices by A, connect it together, and then we get the resulting set. It's going to be a similar thing for the Minkowski sum. So this is what it looks like. And basically we're taking the convex hull of all combinations of sums of the vertices. So let me show you visually what that looks like. So we have our set P, we want to add it to set Q. And basically what we need to do is we need to take every combination of a sum of a vertex for the first one and a vertex for the second one. And so basically what we're going to do is you can imagine it's kind of equivalent to taking this polytope here and moving it to each vertex of Q. And now what we can do is we can say like, okay, if I summed these two, I'd end up here. If I summed this one and this one, I'd end up here. And this one and this one, I'd end up here, and so on. So it's like equivalent to taking all of those individual sums of the vertices. And then we need to trace out the convex hull of this new shape. So we just kind of trace out what we end up with there. And that gives us the Minkowski sum. Any questions on that one? Yeah.
Maybe I'm just like getting a little confused by the visual time.
So basically what's happening here is we're saying for all combinations of V1 and V2, where these are vertices of our sets P and Q, we want to add V1 to V2. And so one way to think of that is to say, let's say I wanted to add this vertex to this one. That would be like taking this and adding on this, so it's like moving this one to here. Let's say I wanted to add this one to this one. Well, that's going to end up over here. And so the way that it ends up kind of looking is it's kind of equivalent to is if you took this and you put it on top of each vertex, and then you looked at all of these resulting vertices, and you computed the convex hull of those. So that's what we're doing. Yeah.
I think the question is that the top left of red the left vertex, left bottom
Yes.
vertex should coincide.
The question is that my slides have an error. Yeah, okay. Thank you for pointing that out. It should have been like that. Yeah, thanks for that.
Oh,
Yeah, I just put it on the wrong spot. Which is a bummer because I had such a cool animation, but oh well. I'll fix it for next time. Okay, so yeah, this is actually not the resulting sum. The resulting sum is like that. But yeah, thanks for pointing that out. Okay. Okay, so now what we can do is we can start thinking about the complexity of doing all of this in terms of the number of vertices. So when we did the linear transformation, we started with 4 vertices here, v1, v2, v3, v4, and we did the linear transformation and we ended up again with 4 vertices. So doing a linear transformation doesn't really change in general the number of vertices that we have for our set. But when we do a Minkowski sum, we had 4 vertices on this one, we have 4 vertices on this one, and then if we just look at the number of candidate vertices, because we're taking the convex hull of everything, again, don't look at this, it should be over here, but the point still holds true that there's like 16 candidate vertices now that we need to take the convex hull of. So we know that the number of vertices in our new shape is going to be bounded by that number. It's going to be less than or equal to 16. And in general, it's going to be less than or equal to the number of vertices for P times the number of vertices for Q. Okay, so if we kind of summarize that here, we can look at what we need to do for our linear reachability. So at every time step, we had this equation here, and it had 3 linear transformations in it and 3 Minkowski sums. And so we can look at this and try to understand, like, what is the maximum factor, the maximum amount we could increase our number of vertices in our reachable set by just like applying this equation to RD minus 1 to get RD. And so the linear transformations don't really matter much because, again, they don't change the number of vertices in our set. But we're doing these 3 Minkowski sums, and specifically we're doing RD minus 1, XO, XA, XS. And so we're going to end up multiplying all of those together. And so we know that the number of vertices for our reachable set at the next time step is bounded by this number here. And that's just for like one time step, but let's go all the way back to when we started from our initial set. And then we can see we need to do this for every single depth. So every time we do another one, we're going to multiply by this number again. So we're going to go all the way up to depth d, that's now in the exponent. And what we've basically shown is that there's kind of this exponential growth in the bound on the number of vertices with the depth. And typically when we see exponential growth, we don't like this, that's not good. Because we're going to get, especially for like high dimensional systems, we're going to get really huge polytopes with like lots of vertices, not huge volume wise, but like lots of vertices for these polytopes as we increase the depth. And so that can be really difficult if you, for example, have like memory constraints or like generally computationally, this can get blow up quite quickly. So one thing that we can do about this is use something called a zonotope. So this kind of motivates the idea for this thing called a zonotope. And zonotopes are a special type of polytope. So not all polytopes are zonotopes, but all zonotopes are polytopes. And they're represented as the Minkowski sum of a set of line segments centered at some point. So here's like the math for it. And if you're anything like me, the first time you saw zonotopes, or the first time I saw zonotopes, this is what you look like right now. I was just like, what is this shape? This doesn't look like anything to me. Like, what are zonotopes? I don't understand this. That's kind of how I felt. So let's build a zonotope here. So like I said, zonotopes consist of these things. It consists of a center point and then a list of generators. And these generators are just vectors. So here we're going to say that we have 3 different generators. And it's the Minkowski sum of the center with all of these generators. So let's look at just one of these generators for now. Let's look at the blue one. And we're going to take the Minkowski sum. And we actually, for zonotopes, we take the Minkowski sum of the positive version of the generator and the negative version. So we're going to need the one going in the positive direction and then one going in the opposite direction. That's just how they're defined. So we're going to take our center point, and then if you remember when we took a Minkowski sum, we took each vertex of the thing we were trying to add it to, and we added on the shape that we were trying to add. So here we're trying to add this line segment. We only have one vertex right now, it's the center point, and so we just add it in both directions to the center point. And then when we took the Minkowski sum, we traced out the convex hull, so we can just trace out the convex hull of this, it's just a line. And our new set now is just a line. So now we've used, yeah?
Sorry, can you repeat what the generators, like just what are the building blocks?
A center and a list of generators, that's how they're defined. So you just have to pick those. Okay, so now we've used the first generator. Now we're going to go to another generator. So let's go to this pink one. And we're going to do the Minkowski sum of this shape we have now with this pink generator. So we're going to add this pink generator to all of our endpoints, or all of our vertices of our current set. So that's what this is doing here. And then we trace out the convex hull of our new set, and then we get this purple set here. And now we have one generator left, so we're going to do the same thing. We're going to add it to all of the vertices of our current set, trace out the convex hull, and then here's our zonotope. And it turns out if you picked any order for those generators, you'd end up getting the same shape when you trace it out, yeah. In this case, it's 2D because our generators are 2D. Just because they're 2D, like if I had picked 3D generators, then we could be going in different directions and stuff. Yeah, I'm just showing 2D for now. But these could be, arbitrary dimensions. Yeah. Yeah, okay, so that's how you get a zonotope. I still think they're maybe a little bit hard to visualize because even from these generators, I don't know if I'd be able to picture this, but that's in general what's going on with the zonotope. Okay, but what's nice about zonotopes is that it turns out the operations for them when we do linear transformations and Minkowski sums end up being a little bit nicer than like the generic operations for polytopes. So when we do a linear transformation of a zonotope, for example, we want to multiply the zonotope by some matrix A, and so all we have to do is multiply the center by A, and then multiply each of its generators by A, and that gives us the new zonotope. For a Minkowski sum, what's kind of cool is we just add the two centers together, and then we just concatenate the list of generators for each of them. So we just have now both sets of generators as our generators for the new Minkowski sum zonotope. And so what's kind of nice about this is that just like with polytopes, the number of generators stays the same. So now we're thinking in terms of how many generators we're going to have to keep track of to represent this shape instead of how many vertices. And so the number of generators stays the same for a linear transformation, but for the Minkowski sum, the number of generators grows linearly now. So the number of generators that the previous set had plus the number of generators that the new set had is going to be the number of generators in the Minkowski sum. So we're not multiplying anymore, we're adding things, which is much better. So it's not exponentially like before, and that's why zonotopes in general can be much more computationally tractable to work with. Yeah.
Do these operations require that our generators are, I guess, like symmetric about our center? So like you said, we have to consider that it can go in the negative. I guess this generator is also in the negative direction.
The generators...
I guess I'm trying to figure out, is this requirement about this like symmetry part of the definition of a generator or part of the sort of the assumptions we need?
Yeah. Okay, if we look at the actual math definition of a zonotope, it's like alpha times this vector g, and alpha goes between -1 and 1, so that's how you get the like both sides of it. Regardless, yeah, it's like part of the definition. Yeah, but the point you're making is interesting, which is that zonotopes are symmetric about the center always. So that's why not all polytopes are like that. So not all polytopes can be written as zonotopes. So we can't always do this type of thing. Okay, and one other lovely thing about zonotopes is that the beloved hyperrectangle is actually just a special case of a zonotope in which the generators are aligned with the axes. And so hopefully many of you have seen hyperrectangles before, at least rectangles. So in 1 dimension, a hyperrectangle is just a line. In 2 dimensions, it's a rectangle. In 3 dimensions, it's like a rectangular prism. And in 4 dimensions, I don't really know, but you can do your best to try to visualize it. And more dimensions as you keep going up. We can keep going up, but in general, I don't know how to visualize that. Okay, so that's the types of polytopes that we have. We have this wonderful class of things called polytopes. Some subset of that is zonotopes, and then a subset of zonotopes is hyperrectangles. Okay. All right. So if we go back now to this problem, we had this exponential growth bound in the number of vertices. So one thing we saw is that we could use zonotopes instead to help us with this, and now that kind of resulted in a linear growth in the number of generators we were keeping track of. But sometimes we can't do that, because sometimes, like I said, not all zonotopes are polytopes, so maybe our polytopes for our initial set and whatnot are not represented as zonotopes, and then we can't do this kind of thing. And so another option is to use over-approximation. So everything I showed you up to this point is exact. So these sets that we get will be exactly the set of points that we could reach, and all of them are reachable by some trajectory. And now what I'm going to talk about is over-approximation, where we can define this new set. When we talk about over-approximate sets, we'll often put this kind of bar on top of them. So if you see the bar, that means over-approximation. It's an over-approximation if the true set that we're over-approximating, so the P, is a subset of that set. So this operator here just means subset or equal to. So for example, let's say that we have this set P. An over-approximation of P might look something like this, where everything in the blue set is also contained within the purple set. Okay, and so one idea here is we have these polytopes with lots and lots of vertices, and so what if we just over-approximated it with a polytope with fewer vertices, and then we don't have to deal with as many vertices? But does that really help us? It does help with having too many vertices, but what does this do to our guarantees as we're trying to understand the set of states that are reachable? So let's say that this was our reachable set, and we said we don't want it to intersect with this kind of set of bad states here. So let's say we only know the over-approximated version. We don't know the true reachable set because we didn't want to keep track of all the vertices for it. Can we still conclude that this system satisfies the specification given this scenario here from our over-approximated reachable set? Yeah, we can, because if the over-approximated reachable set doesn't intersect with our avoid set, and we know that the true reachable set is contained inside here, then there's no way that the true reachable set intersects with our avoid set. So we can conclude that this works. Okay, what if we had this? Well, we certainly can't conclude that it satisfies the specification because we've overlapped with the avoid set, so there might be states that could reach it. But could we conclude now that it doesn't satisfy the specification? No, yeah, we can't conclude that it does not satisfy the specification either, because we don't know what the true reachable set looks like. So it might be that the true reachable set is still some like subset of this set that doesn't intersect with the avoid set, and we don't know. We like don't know either way, so we just can't really draw a conclusion from this. Okay, so what does this do to our guarantees? If the over approximate reachable set does not intersect with the avoid set, we can still make a guarantee. We can still conclude that the system is safe. But if the over approximate reachable set does intersect, then we can't conclude anything. We don't know if it's safe or not. Okay, and then we can do this in practice by like every few iterations, we'll then just over approximate the reachable set with a set that has fewer vertices, and then we won't have as many vertices to keep track of. So here's the line in the algorithm that does it. And surprise, surprise, lazy sets has got us covered. It just has this over approximate function where we give it some epsilon, and it will just return an over approximate set with that kind of error bound on it, which is wonderful. And if you want to know how that over approximate algorithm works, you can check out this section in the book. We talk about how they actually do it. And I guess since we're running out of time, I'll pick up next lecture probably here. This is what it looks like. And we'll talk about kind of the basic building block of that method for over approximating sets. So yeah, I think we'll wrap up here, and I'll see you on Thursday.